Good morning, my dear students. In the previous class, we discussed about the relation between the electric field and potential. And for that, we get the expression that is E is equal to minus dV divided by dr. From that relation, we used to say that electric field direction is always in the direction of the decrease in the potential. In today's class, we will talk about one important concept called electrostatic potential energy of a system of point charges. It is similar to that of the electric potential. Right here, electric potential energy of a system of point charges. Point charges. So this potential energy of the system of point charges is the amount of work done. Is the amount of work done in bringing the charges from infinity to their present configuration, to their present locations. As the name indicates, potential energy. It is the energy possessed by the body by virtue of its position or configuration or location. In the same manner, potential energy of a system of point charges is the work done in bringing a point charges or a system of charges from infinity to their present configuration or present location. That is called the potential energy of the system of point charges. I write the definition here. The amount of work done, in bringing a point charges from infinity to their present configuration, or location. Right? Suppose that the charge is present somewhere at infinity, and if I want to move the charge from infinity at this point, say that A, I will move this charge from infinity to this point, say Q1. Alright, so I have brought a charge of Q1 from infinity to this position. So now it has some potential energy now. This charge has some potential energy because it has some position. It has located at a certain point. So we call it this charge has potential energy. In the same manner, I can bring one more charge Q2 and place it here at point B, that is Q2. So work must be done to bring that charge. If suppose that initially when I moved a charge Q1, when I move the charge Q1 from infinity, there is no other charge present. There is no other charge present, so the work done is 0 here. Because initially there was no any electric field present. Now when I place this charge Q1 at this point, it has electric field as well as the electric potential. So I can find the electric potential at point P now. At a distance R12, it has some potential, it has some electric field. But if there are no charges are present at this point, I cannot say that there is any electric potential present or electric field. Only if I bring a charge from infinity at one position, then this charge can have electric field as well as the electric potential. But when I move the other charge Q2 and bring it here at this position B, then this Q2 charge experiences the force because of this charge electric field. Then I have to do some work against this electric field because there is already field is present, and we know that work done is given by W is equal to VQ. So this W is the work done to bring this charge from infinity to their present configuration. Alright, this V is the potential due to this charge. This V is the potential due to this charge. When I move the charge Q2 from infinity to this point, there is already the existence of the electric field. So in the existence of the electric field, I must do some work to bring that charge. So that work is done by W is equal to VQ R. Say that R is the position vector. R is the position vector. Right? So here we will find the derivation for the potential energy of the system of point charges and the absence of the electric field. The absence of the electric field. So here, write here potential energy of a system of 2-point charges. 2-point charges. 2-point charges in the absence of external electric field. In the absence of the external electric field, we have the derivation for this, a small derivation. Usually asked in the examination for the 3 marks. Derive an expression for the potential energy of the system of 2-point charges in the absence of the external electric field. As I said that when a charge is moved from infinity to this point, say that point A, initially there is no charge present, hence there is no electric field. So this charge is moved from infinity, this point A, say that Q1 charge is moved at point A, there is no work done. There is no work done. Why? Because initially there is no field. There is no field. Initially there is no field. Why? Because there is no charge present. Only when I bring the charge from infinity to this point, now it has some electric field. Now it has some electric field. It has certain potential at this point. It has some potential at this point. Now if suppose that I will bring one more charge Q2 from infinity to this point, say that at point B, there is an electric field now. There is a electric field. Now there must be the work is done against this electric field. Because this charge has some electric field around its region. This charge has some potential at some other point. So work must be done to bring the charge Q2 from infinity to this point. So using this concept, we will derive the expression for the potential energy of system of 2-point charges. Okay. So here, say we will consider a system of 2-point charges. Consider a system of 2-point charges Q1 and Q2 at a distance R12. A distance R12. So here there are two charges. Right? They are separated by distance R12 now. Right? There is one charge Q1, a charge Q2. They are placed at the respective points A and B. Right? There are two charges Q1 and Q2, and separation between these two is R12. R1. Right? So here I write the work done to move charge Q1 at A is W1 is equal to 0. W1 is equal to 0. Why I can write that this W1 is equal to 0? Work done is 0 because initially when I move that charge, there was no electric field present. Initially there is no electric field present. Say that I am bringing the charge from infinity to this point A. Then there is no electric field is present. So no work is done. Therefore I write here initially there is no electric field. There is no electric field. So no electric field means what? No work is done. Electric field, if absent, then there is no work is done. Now the work done to move a charge Q2 at B is the work done to move a charge Q2 at B is given by W2 is equal to V1 into Q2. To get here, the work done to move a charge Q2 at B is W2 is equal to V1 into Q2, where V1 is the electric potential. V1 is the electric potential at B due to charge Q1. Due to charge Q1 at a distance R12. Right? See here, when I move the charge from infinity to the point A, there is no electric field present. When I bring this charge at Q1, now there is certain electric field is present now. When I bring another charge Q2 from infinity at this point B, there is electric field. The work must be done here. Work must be done to bring that charge. You get here. When I bring this charge Q2 from infinity, now there is already charge is present Q1. And due to this charge Q1, there is electric field. And due to this charge Q1, a charge is placed. The potential at a certain point is present now. So the work done to move the charge Q2 from infinity at B is given by W is equal to V1 into Q2. Therefore, V1 is given by 1 by 4 pi epsilon naught Q1 by R1. 1 by 4 pi epsilon naught Q1 by R1. Right? So its absolute value W2 is equal to what is V1 here? It is 1 by 4 pi epsilon naught Q1 by R12 into Q2. Okay? Now, this work done is equal to the potential energy of a system of charge. This work done is equal to the potential energy of the system of charge, that is U is equal to W1 plus of W2. So this total work done is equal to the potential energy of the system of charges. So what is W1? It is 0. What is W2? It is 1 by 4 pi epsilon naught Q1 Q2 divided by R12. Q1 Q2 divided by R12. Therefore, we write U is equal to potential energy. U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12. Q1 Q2 divided by R1. This is the potential energy of the system of 2-point charges in the absence of the external electric field. Alright, so U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12. If suppose that a third charge is present now. If third charge is present, what will be the expression? What will be the expression for this electric field or the potential energy of the system of charges? Say here, we consider a third charge. For third charge, I will draw the diagram here, a small diagram. Say here, this point A, it is point B. At point A we have Q1, at point B we have Q2. The separation between these two is R12. Right? Now the third charge is present at C. This is point C. We call it Q3. So distance is R13 and it is R23. Right? Okay. Now consider a third charge Q3 at C at a distance R13 from Q1 and R23 from Q. Okay. Earlier we have seen that there are two charges separated by distance R12. Now there is a third charge is present at C now. At a distance R13 from Q1 and R23 from Q. Now, when I bring this charge, the potential at C is the potential at C is, and this B is equal to 1 divided by 4 pi epsilon naught, 4 pi epsilon naught q1 divided by r12, sorry, q1 divided by r13 plus q2 divided by r23. Look at here, right? This is the potential due to these two charges, q1 as well as the q2. Separately we can write like this. Usually potential you can write as 1 by 4 pi epsilon naught q1 by r13 plus 1 by 4 pi epsilon naught q2 by r23. What is common here? 1 by 4 pi epsilon naught. What remains inside? q1 by r13 and q2 by r23. That is what I have written here. So here the work done to move q3 from infinity at C is, that I will call as the W3. I will call as the W3. So it is W3 is equal to V into Q3. V into Q3. This is the potential due to these two charges, Q1 as well Q1 divided by R13, or you can say the R31. Call the R31. Right? R31 plus Q2 by R23. This is the potential due to these two charges, Q1 and Q2 at point A and point B. Now, when I bring the charge Q3 from infinity at C, then the work is done is what? V into Q3, because V is the potential due to these two charges into charge Q3. So what is the value of V here? So V is nothing but what? 1 by 4 pi epsilon naught Q1 divided by R31 plus Q2 divided by R23 into Q3. Or W3 is equal to 1 by 4 pi epsilon naught Q1 Q3 divided by R31 plus Q2 Q3 divided by R23. Q1 Q3 divided by R31 plus Q2 Q3 divided by R2. So now there are this work done. There are two work done now, three work done now. W1 is the work done to move the charge Q1 at A. W2 is the work done to move charge Q2. W3 is what? Work done to move charge Q3 from infinity at C. Right? When I add all these three work done, we get the total energy. Right? So this total work done is equal to the total work done. The total work done is equal to the potential energy of a system of three charges at points A, B and C. A, B and C. Therefore, U is equal to W1 plus W2 plus W3. Substituting the values of W1, W2 and W3. What is W1? It is 0. What is W2? It is 1 by 4 pi epsilon naught Q1 Q2 by R12. What is W3? It is 1 by 4 pi epsilon naught Q1 Q3 by R31 plus Q2 Q3 by R23. This is the total energy. I will write here that is the final expression. That is total energy U is equal to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught into the bracket. W1 is 0, W2 is 1 by 4 pi epsilon Q1 into Q2. So Q1, Q2 divided by R12 plus these two, that is Q1, Q3 divided by R31 plus Q2, Q3 divided by R23. This is the total energy stored in the system. Right? Usually in the examination they ask for this expression. There are an expression for the system of 2 point charges in the absence of the external electric field. This expression for the 2 point charges, system of 2 point charges, and this expression is for the system of 3 point charge.